Hello, my name is Tomas Petricek and I want to talk about programming through the lens of architecture, design and urban planning. When we talk about programming, we use quite a lot of different metaphors. We talk about writing code as if we were writing any other ordinary piece of text. We talk about software engineering as if programming was like building bridges. And I'm going to add architecture, design and urban planning to this vocabulary. But first, let me explain why does this actually make sense. Programming is a lot about dealing with complexity. I'm going to refer to Jane Jacobs, who wrote this excellent urban planning book in the 1960s, The Death and Life of Great American Cities, where she explains exactly why urban planning involves a lot of complexity. So Jane Jacobs says, we may wish for easier all-purpose analyses and for simpler, magical all-purpose cures, but wishing cannot change these problems into simple matters, no matter how much we try to evade the realities and to handle them as something different. So Jane Jacobs very much realizes that architecture and urban planning has to deal with a lot of complexity in the system. And programming is very much the same. So that's one of the reasons why I think it's worthwhile looking at what's been done in this field and see what we can learn. But the interesting thing in Jane Jacobs is that she actually elaborates on what kind of complexity a city is. So what kind of problem city is. Here, Jacobs uses or refers to a paper that analyzes the history of science and looks at different eras in the history of science, where scientists first learned how to tackle problems of simplicity, which are problems where you have a full analytical solution. So Newtonian physics, for example, you can fully analyze everything. More difficult, more challenging problems are problems of disorganized complexity. So this is things like movement of molecules inside gas, where you can't precisely simulate every single molecule, you can't calculate that, but you can apply some statistical methods to simplify and reduce the problem. And the most interesting problems in sciences, this is things like genes, gene expressions, are problems of organized complexity, where you really have a lot of different things going on and they're very complex processes, but there's no way to reduce the complexity. There's no way to get rid of it and abstract it away. And Jane Jacobs points out that understanding cities or urban planning is exactly dealing with these problems of organized complexity, where there's lots of different processes, they're all interacting in subtle ways, and you just can't reduce or sort of abstract away, just work with average inhabitants of a city. Now, interestingly, a very similar structure, very similar categorization exists about software systems. And this is due to Dave Parnas, who wrote in 1985 a paper that looks at the US anti-ballistic missile software efforts, attempts to build a system, and tries to argue why this is very hard, or possibly why such a system cannot even be built. And he opens the paper by looking at the kind of problem that software is. And this has very similar structure to what Jane Jacobs is doing. So Dave Parnas points out that the easiest systems to deal with, the ones that engineers know how to cope with very well, are analog systems, where they operate within some safe operational range, and a small change in the inputs will cause a small change in the outputs. So if you know that individual components are well behaved, then you can pretty much understand the whole system. Now, engineers have also learned how to build digital systems that are repetitive. So an example here is the CPU. This is a very large system which has lots of different states, but because it's very repetitive. It's sort of built up from small repeated components that are simpler. You can analyze the individual components, and then from the sort of analysis of those individual components, make sense of the whole system. Now, the reason why software is difficult is that software is a problem of organized complexity. So there's a large number of states, but they're not result of some sort of repetition. They're just all unique, very different states. And it's not analog, meaning that a small change can completely change. Small change in input can completely change the pattern of the behavior. So just like in the case of Jane Jacobs' analysis of cities, here we have systems that are not only you can't fully analyze them, but also there's no way to sort of simplify and reduce the complexity. With a lot of effort, you can fully analyze sort of increasingly bigger software systems, but once it gets beyond some threshold, it's just going to be too much. So that's why I think looking at urban planning is a really interesting perspective, because it's exactly an area that is already learning since 1960s how to deal with these problems where you can't reduce the complexity of the system. And Jane Jacobs wrote her book as a response to the sort of development in urban planning and city planning prior to the 1960s, earlier theories which were always trying to do some sort of simplification. And her counterpoint to those theories was saying the pseudoscience of city planning and its companion, the art of city design, have not yet broken with the specious comfort of wishes, familiar superstitions, oversimplifications, and symbols, and have not yet embarked upon the adventure of probing the real world. So Jane Jacobs was really seeing the current theories of the time as something that uses these oversimplifications that are just not really applicable to the real world. And when I look at some of the things that we do in programming systems, programming languages, I think we might be actually still in the era not yet embarked upon the adventure of probing the real world. So Jane Jacobs was referring to various utopian urban planning ideas like Corbusier's Villa Radies or Ebenezer Howard's Garden City idea, which were all sort of coming up with a reasonably logically sounding visions of how you sort of organize a city by grouping various functions together and having large boulevards where cars can get from any point to any other point, and to balance for that you'll have lots of different parks. All those theories sounded like they could possibly work, but in practice they didn't. And what Jane Jacobs was doing was that she was actually looking at cities that do work, or places in cities that do work. And her book is this amazing analysis of little details in two places, in Greenwich Village in New York and North End in Boston. And she's sort of looking at the street life, as she calls it. So how the fact that there's mix of functions in the city contributes to the safety, because there's always people walking around from one place to another throughout the whole day. And so her analysis is really sort of taking the places that from her own personal experience work and looking at why that's the case. In programming, I think we've got plenty of utopian programming system ideas that are based on a nice idea, but if you look at some of the analyses that people have done, they actually prove to be more tricky. So abstraction is one of them, and there's a paper in recent Onward essays about fatal abstraction where this actually doesn't work. We all love information hiding because we think it will help maintainability of our systems. But again, there's counterexamples where information hiding actually prevents later evolution of a system. And in programming languages especially, we all love formal models, but just like the formal theories of urban planning prior to 1960s, the formal models we use are often missing crucial aspects about the programming systems that we're actually dealing with. So what is Jane Jacobs' answer to this problem? How should we actually understand complex systems, and how should we design cities that work? For her, the key idea is really understand the city as it is, as the real system with all its messiness and complexities. And she says, in the case of understanding cities, the most important habits of thought are, first, to think about processes, second, to work inductively, and third, to seek for unaveraged clues involving very small quantities which reveal the way larger and more average quantities are operating. So her approach is to look at a very specific thing in the city and analyze it and see what are the more general lessons that we can learn from that. Her specific example, one that's very nice, is this chain of bookshops that operates all over New York, and it has several branches that are all open until 10 p.m. in the evening, except for one branch in, I believe that was Brooklyn downtown, which closes at something like 7 p.m. And that's one example that really illustrates that one aspect of the city is very different, because that's where nobody is there after 7 p.m. There's nobody walking around to buy books. So that one simple example is actually sort of reveals a bigger truth about the system. So my first call to action from this talk is that I think we should follow Jane Jacobs and study programming systems that actually work in their full complexity, starting from the small details that can reveal what is it about a system that really, really makes it work. And I think it's important to sort of overstep our own assumptions and beliefs about what are the programming systems that work, because we all have our favorites. But if you look at some of the interesting technologies that actually are working in the industry, like JavaScript, there might be interesting reasons why that works that are beyond the scope of what we normally talk about in programming languages research. Another area where I think we can learn from urban planning is related to conceptual coherence, which is a term coined by Fred Brooks in the Mythical Men Month. Conceptual coherence is basically this idea that a system is fully comprehensible. So Fred Brooks says that conceptual coherence dictates that the design must proceed from one mind or from a very small number of agreeing resonant minds. The point here is that if you're building a large system, if it sort of is designed by multiple people who will all understand it differently, then it will not be conceptually coherent, it will not be comprehensible. So there's this sort of mismatch between the user who has to be able to make sense of it and potentially large number of programmers who are building the system. Or as Fred Brooks says, any product that is sufficiently big must be conceptually coherent to the single mind of the user and at the same time designed by many minds. So for Fred Brooks, the whole issue is how do you actually design a system so that it all makes sense together, it's all sort of understandable using some reasonable rules or some logic behind it. And for him, the issue is that this works if it comes from a single mind, but once you start building things that are too big for a single mind, then it's harder to achieve. Now, if you look at cities and urban planning, then there's different kinds of cities, I have two example maps here. One is more or less conceptually coherent. So this is Manhattan, New York, where you have the nice logical grid with street numbers that are easy to understand. And on the other hand, I have a map of Prague, which is evolved very much through an evolutionary process and has no sort of overall structure, at least not in the downtown part that you can see here. Does this mean that making sense of Prague is impossible? So here I'm going to refer to James Scott's Seeing Like a State, and Scott points out that the fact that the layout of the city, like Bruges, having developed without any overall design, lacks a consistent geometric logic, does not mean that it was at all confusing to its inhabitants. So Scott is looking at the design of cities and urban planning as well, and he points out that you don't really need that sort of consistency and coherency to make sense of a city. And in fact, the relative illegibility of some urban neighborhoods has provided a vital margin of political safety from control by outside elites. So not only is the sort of messiness of a city something that's not a problem to its inhabitants, but in some cases it's actually quite valuable. It's helped them in many ways to sort of confuse the outsiders who are trying to impose various structures and control over the city. So the lack of coherence isn't necessarily a problem, but of course the inhabitants, the people who live in the system, have to be able to understand it. And in cities, this is achieved in various ways. One useful analysis of how people actually navigate around cities, how this works, is a book called The Image of the City by Kevin Lynch. And in that, Lynch points out that there are various structures in a city, like paths or landmarks, that are sort of used for navigation. So you might have a landmark, like a castle that's visible from many different parts of the city, and you will immediately know where roughly you are. You have different districts, which are distinguished by, say, different style of buildings. You have various paths through the city, which could be a road or a cycle path, or something like an underground network. And I think this is something that's very much relevant to programming systems as well, because if you have a very large software system, you can't really have this precise map with every single street on a grid to navigate and sort of understand every aspect of the system all at once. But what you might very well have is a system where you know some general districts, some general parts of it, and you can you know how to navigate between them, you know how they're related through something like the metro system in Prague. And that gives you a sort of basic structure of moving around, understanding how different components might relate. So there goes my second call to action of the talk, which is that I think we should start thinking about understandability, not about conceptual coherence. And by understandability, I really mean something that's much more dynamic than what we see in, say, conceptual coherence. With conceptual coherence, the idea is you'll read the documentation and then you'll suddenly understand the whole system. I think understandability is something that can come more from interacting with the system, from sort of feedback, and from a sort of dynamic process where, just like when you live in a city, you might know some neighborhood, and then when you need to explore some other neighborhoods, you have a ways for doing that. And I think that might be a much more interesting and useful way of dealing with complexity in large software systems. The third point I want to talk about is about adaptable software. And this is inspired by Stuart Brand's work on how buildings learn, which is this analysis of what happens to buildings once they're built, looking at different kinds of buildings and pointing out that the evolution is different for each of those. And Stuart Brand starts by pointing out that almost no buildings adapt well. They're designed not to adapt, budgeted and financed not to, constructed not to, administered not to, maintained not to, regulated and taxed not to, and even remodeled not to. But all buildings adapt anyway, however poorly, because the usages in and around them are changing constantly. And when you read this, I think you will immediately see why I'm bringing this into a discussion about software, because software, I think when we design software, we're very often sort of designing it for the situation that we currently have at hand. Of course, there's various hopes that our programming languages allow the right kind of extensibility, but we never really know in what directions is the system going to evolve and change. And of course, just like buildings, software will adapt, however poorly, because the usages and the context and environment around it is changing. So what is Stuart Brand saying that we should do? He's actually talking about different kinds of buildings, and for different kinds of buildings, you might have different kinds of strategies. But one of the, or two of the points in the book that I found very interesting that I think are equally applicable to software are, first, that the point that new buildings teach bad maintenance habits, and that's because when you build a new building, it works, and for several years it will need no maintenance, and so the inhabitants are going to stop paying attention until eventually things will start breaking, and then they don't have the habits, they don't know how the maintenance should be done. And I think in software this is equally relevant. We do actually have this idea of cow's monkey for developing distributed systems, which I think is sort of part of the answer here of teaching good maintenance. The other interesting point made by Stuart Brand is that the maintainability very much depends on materials. And he's very much arguing for materials that have this quality that they look bad before they go bad. So a wooden siding on a house is an example, because when you look at the house, you will immediately see in what condition the siding is, and you will see that this is something that's going to break and not work very well much earlier than it actually breaks. And when houses instead get covered with vinyl siding, that is something that looks great, but you don't see that the surface behind it is slowly rotting. So this is, I think, an interesting challenge for software. The other interesting point from Stuart Brand is that one particular kind of architecture that's called vernacular or unself-conscious architecture is works quite differently. So this is when you have things like New England farmhouse, which is built basically by doing exactly the same thing as all the other farmhouses in the area, with some minor tweaks by the current owner because they have some specific requirements. But you're always basically following the same structure and making adaptations over generations. So that's what you could call design without the reinvention of the form, because the basic form always stays the same and it's just small adaptations. In contrast, when we're building software, we're pretty much always starting by reinventing the form. And that I think is a sort of interesting opportunity. How could we actually design software so that we're not reinventing the form from scratch, but we're sort of adapting or building on what's already there? And I think this actually does happen in some areas of software engineering. I think it happens in areas where you have large systems that are mostly evolved or applied by configuration, by sort of making all those small tweaks, or in systems that make it very easy to copy, paste, and reuse existing materials, like HyperCard or the 1990s web. So my third call to action from the talk is to really think about the materials and the way the things, the stuff from which we are building software, and invent materials that age well and allow adaptation. So by that I mean allow adaptation. I think that involves a lot of sort of having access to how the thing is built so that it can be modified without having to be completely rewritten. The question about materials that age well, I don't have an answer to that one, so this is still an open question. So my final point is, how do we actually get to a point where architecture, design, and urban planning is the way we think about software? And I think this is already a very nice and very useful way of thinking about software, but what is it going to take for this to become mainstream? And here I think we can draw an interesting parallel with the history of software engineering, where the way of thinking changes not so much when someone comes up with a new idea about how to think about software, but more when there's some outside external circumstance that makes that change happen. In 1960s or 70s, the birth of software engineering was really a response to the increasing computer availability, when more and more companies needed to build software, and the small number of expert programmers that were available wasn't enough to do that. So they needed to sort of borrow the factory and production model to come up with a way of building software that scales more. In 1990s, the various lightweight software development methodologies were again a response to the fact that various sort of market forces were making software development faster. You had to build an application to respond to what your competition was doing in a much shorter time frame, and that required a different thinking about software. I think for architecture, design, and urban planning, we might just have to wait for another change in the socio-technological context. So keep an eye on what's happening in the industry, and hopefully at some point soon there will be a change that really sort of naturally makes us think of software as more like an architecture, design, and urban planning. Thank you.